So what happens to your brain activity when you go under? Neuroscientist Emery Brown is measuring the line that separates being conscious from being unconscious.
I want to guarantee my patients that when I say you're unconscious, you're not going to perceive pain. You won't be moving around. You won't remember anything that's occurring. Your heart rate and blood pressure and other physiological systems will be well controlled.
The patient is undergoing surgery. But before the surgeons can operate, the anesthesiologists have to put her under, render her unconscious with special drugs.
I'm starting to give you medicines that might make you feel kind of drowsy.
Look straight ahead. Look straight ahead. So her eyes move as we'd expect them to move.
So you're moving her head, but her eyes stay straight.
All right, honey, we're going to have you breathe.
Breathe some
Little
oxygen for a
oxygen.
minute. Can you see my finger here? Follow with your eyes. And if you can't follow it anymore, tell me, all right? Can you hear me? See, her eyes are fixed now.
Yeah,
You see the EEG has a large, slow oscillation. See that?
yeah.
Her brainstem is out.
That's out, that's it.
When you go under, it can feel like 1 second you're here and the next, you're out. What's going on in the brain when this happens? Emery uses a device called an EEG, a set of electrodes that rests on the scalp and detects electrical activity in the brain. That activity comes in the form of waves.
The brain generates brain waves, or oscillations. And they're oscillations that we typically see when someone's conscious.
These brain waves are measured by their frequency, how fast the waves come and go, and by their amplitude, how small or big the waves are.
I look at your EEG. When you're awake, you're going to have a very rich response. When I anesthetize you, it goes away. And so the difference between those two states represents the transition from being conscious to the unconscious. See the oscillations? See how they're really big now?
And before, so they were just sort of little...
Yeah, exactly.
Yeah.
When you're awake and fully aware, your brainwave activity is diverse and dynamic. It looks kind of like an exciting conversation. But when anesthesia drugs hit the brain, the activity is dramatically reduced to dull, slow rolling brainwaves. The once dynamic conversation becomes an unintelligible hum.
If you alter how the parts of the brain communicate sufficiently, you can make someone unconscious. So that's what the drugs are doing. They're altering the way the various parts of the brain communicate.
There's one region of the brain in particular that acts as a communication hub, the thalamus. It's made up of two parts, each about the size of a walnut, and sits deep inside your brain.
Thalamus is a central way station for all sorts of information processing. Auditory information goes through there, visual information goes through there, pain information goes through there. If I could take out just one brain center to make you unconscious, it would probably be the thalamus, because it's such a central actor in processing all types of information.
After a couple of hours of surgery, the medical team is tapering off the anesthesia drugs. And the EEG reveals the patient's brainwave activity becoming more complex as she wakes up.
She's starting to take some breaths on.
Yeah, open your eyes wide and squeeze my hand.
Consciousness is really having active cognitive processing, being able to think and act.
Surgery's all done, okay?
It's the integration of that information which allows us to start to understand how consciousness is actually formed.
Consciousness can obviously interact with the physical world like we can. We can use drugs to remove it. We go to sleep and we're not conscious, and yet it's tenuous at the same time. We can't say how any specific set of neurons working together produces consciousness.
It's so clear that anesthesia is some kind of change of consciousness, right? The whole brain is there, the pieces are there, but the messages aren't getting through in a way that makes for a conscious experience. And that's the difference between being aware and not being aware.
So the level of communication among brain regions is one difference between being conscious and being unconscious. That means that no single area of the brain is responsible for your consciousness. It's that communication that helps make you, you.
Now let's remember that the left hand is governed from the right hemisphere.
For some people, an entire half of their brain can't really communicate with the rest. These are people who have undergone split brain surgery, and it's as if they have two minds in a single brain.
Now the question becomes, what happens when you allow both hands together to try to solve the problem? And what we find out is that they fight over each other. One hand knows how to do it, and one hand does not, and so they more or less squabble.
The human brain contains two sides, the left hemisphere and the right hemisphere, right? And they are connected by a big bundle of fibers. It's called the corpus callosum. All the communication from one side of the brain to the other has to pass through this fiber bundle.
For some people with epilepsy, a seizure in one hemisphere can quickly spread to the other by way of the corpus callosum. But if that bridge is surgically severed, a seizure can no longer cross to the other side of the brain. In addition to treating epilepsy, these surgeries have also led to some astounding research into how the two hemispheres function.
With your left hand, make me the A-OK sign.
To learn more about these fascinating studies, I met two pioneers in the field, Michael Miller and Michael Gazzaniga. Michael Miller asked me to step into his lab to do a few simple tests, just like the ones he's conducted with patients after a split brain surgery.
So Heather, what you're going to see are two shapes. They're going to come up on the screen. You'll draw the shape on the left side of the screen with your left hand and the shape on the right side of the screen with your right hand. And I want you to draw them as quickly as you can, but at the same time. Okay?
Piece of cake, right?
Oh,
Beautiful. Okay, I'm not sure what you're drawing over here, but
oh.
that's okay.
Did I mention I didn't get that much sleep last night?
The left side of the brain controls most of the right side of the body, and the right side of the brain controls most of the left side of the body.
Because I start out trying to do different things, and then they just sort of like sync up together.
Yeah.
Come on, man.
It's perfectly normal. So, I mean, what's happening is that the motor commands in one hemisphere are interfering with the motor commands in the other hemisphere.
It was basically impossible for me to force my hands to draw two different things at the same time. But for someone whose two hemispheres are disconnected, there's no interference. It's almost as if there's one mind controlling the left hand and a completely different mind controlling the right hand. And it isn't just movement that's split across the hemispheres. Only half of your visual field goes to each side of the brain.
When you're looking straight ahead, everything to the left side of that space goes only to the right hemisphere. And the opposite is true for the right side of the space.
The left part of the brain is where your language and speech centers are. That enables you to talk, enables you to understand language, and all the rest. And the right side of your brain is very important in the evaluation of emotions, evaluation of visual space. I'm going to give you a test.
If you look right at my nose, and I hold up my hands, you tell me how many fingers you see, all right?
How many fingers do you see? You see two, right? Why did you see two? This one went to your left hemisphere. This one went to your right hemisphere, way over on the other side of your brain. How does your left hemisphere know about it? That pathway, the corpus callosum. It transfers that information. Now I'm going to split your brain. And I do the same test. How many fingers do I see?
You see anything else?
No.
Okay.
You see one. You see this one because that goes straight to your left talking hemisphere. This one is still going to your right hemisphere, which has now been disconnected from your left. So your left brain can't talk about this. So you now say you only see one finger, even though your right brain is seeing this finger. It just can't talk about it because the highway that communicates that information has been cut.
Show me with your right hand what you see. Okay. Put it down, relax. Show me with your left hand what you see.
One.
Good.
It's the most remarkable thing to witness. You know, there's this whole other entity in the head that's controlling the body and can understand and remember and feel and think all on its own, completely separate from the other side.
The researchers conducted tests to explore how a split-brain patient's two hemispheres work independently from one another, including a now famous experiment of a patient named Joe.
Look right at that.
By quickly flashing a word to just the left side of his visual field, that word would go exclusively to the right half of his brain, the half that can't talk.
So the only way we're going to know that it registered is if he can write something out, okay?
With his hand that is controlled by his right hemisphere.
Exactly, his left hand. We flash the word Texas.
Look right at that. See anything?
And flash. Didn't see the word.
His right hemisphere is seeing it.
We're seeing it, but the right hemisphere, at this point in his surgery, cannot talk.
Right.
All right, I want you to draw for me that thing upside down.
So he claims to not have seen anything.
Yeah.
Oh my God. Wow. He was able to do Texas upside down.
But what's interesting is he had no idea what he's drawing, and we know because we saw the word.
I can't tell what it is.
Wow.
So then later on, I show him the word again, and I ask a different question about what he saw.
Once again, they showed the word Texas to just his right nonverbal hemisphere. So when asked about what he saw, all his left hemisphere can say is,
I'm aware of a word, I just didn't see what it was.
Draw something that goes with that, a symbol of that.
Oh, wow. So he draws a cowboy hat.
And clearly his right hemisphere knows exactly what he's drawing. Wow. But his left is still confused. It's like doesn't understand that.
Right.
What's that?
Cowboy hat.
Cowboy hat? What was the word?
Texas.
I can't believe it.
Did you see Texas?
No.
The split brain phenomenon suggests that there can be two separated minds, if you will, inside of a skull. The cooperation is on the paper, not inside the head. It's an astounding example of cross-cueing and management of two mental systems into one unified act. And the idea is maybe that's going on in us all the time, too.
Each of us has a sense that we're a unitary being, but actually that belies the fact that each of us, each of our minds, is actually composed of lots of different pieces that are doing different things. And different information can be represented in different parts of that machinery. And so a search for where am I in all of this is a little bit misguided because the I is not such a unitary thing in the first place.
That feeling of unity of me is actually distributed across almost 90 billion neurons. This illusion that there's a single person inside our skulls.